So we're going to talk here about section 5.1 on Riemann sums. Riemann was a Swiss mathematician back in the beginnings of calculus, or shortly after the discovery of calculus. So we're going to talk here first, how do we measure distance traveled? So you may know from your science or physics work that distance equals rate times time. And that's true when the rate is constant. So for example, if you drive 50 miles an hour for 20 miles, then the distance you travel is going to be the 50 miles per hour times the 2 hours. You can see that the hours will cancel and you'll get that you will have traveled 100 miles. Now, there's a geometric representation of this as well. If we have our velocity on the vertical axis and time on the horizontal, then a constant velocity of 50 is going to be a horizontal line. And if we look at along the horizontal axis, if we go 2 hours, then that area underneath the curve is our 50 times 2 is the 100 miles that we traveled. So this idea of area under a curve is one that we're going to explore further here. So I'm going to follow along here with our fundamental theorem of calculus number 1. So this data is printed on there, and I'm going to do the first few questions on that front page together here. So we have that it says a car is traveling, so its speed is never decreasing during a 10-second interval. The speed at various moments is listed in the table below. So we have time in seconds, speed is in feet per second, and again, this is never decreasing. So in part A, we want to answer the question, use the table to help explain why the best lower estimate for the distance traveled in the first 2 seconds is 60 feet. So what I'm going to do here, I want to give a geometric representation, and we'll talk about that a little bit here. So from the information we have in our table, we have that time is here and speed or velocity is on the vertical. Then we can put along here the 2, 4, 6, 8, 10. So we can see our velocities at these various time increments. So I'm going to say, there is 30, and let's just say there is 40, and 50, and 60. And so we're going to, if we plot some points there, at time 0, we know we're going 30. At time 2, we're going 36. At time 4, we're going 40. At time 6, we're going 48. At time 8, we are going 54. And at time 10, we're going 60. So we just know these data points there. And we know this thing is never decreasing. So here's what we know. Now, why is the lower estimate for this, the best lower estimate, going to be 60 feet? Well, we don't really know how these 2 points are going to be connected. Is it a straight line? Does it do something like this? Does it go along here and then just shoot up at the last minute? So if we want a safe lower estimate, we know that the slowest we ever traveled on this 2-second interval is going to be at that 30. So if we look at the area there, if we imagine we went that 30 for the entire 2 seconds, then we would have gone 30 times 2, there's our distance equals rate times time, we would have gone 60 feet. So certainly we didn't travel any less than 60 feet. That's the least amount we could have gone. Okay? And why is the best upper estimate going to be 72? So here, imagine that you went the fastest you went on that entire interval for the entire interval, which we didn't, but that would be certainly a ceiling, an upper estimate. Certainly we didn't go any further than the 36 times 2, which is 72 feet. So that's why a safe or a good lower estimate would be 60 feet, and an upper estimate would be 72. So now, how about if we do a lower estimate for the entire 10 seconds? Well, the idea behind this is let's take that lower estimate that we got for the first 2 seconds, and then we'll repeat that process for the next 2 seconds. On the next 2 seconds, so the first 2 seconds, we know we traveled at least 30 times 2 feet. On the second 2-second interval, we know the slowest we ever went was 36. The fastest we ever went was 40, so certainly we went at least 36 times 2 feet. And again, for the next 2 seconds, till we get till 8, we could imagine that the slowest we went during that whole interval was 40 feet per second times the 2 seconds. And again, if we went 48 times the 2 seconds, and finally the 54 times the 2 seconds. And so if we add all of those up, we're going to get, I'm going to pause it here and just throw it on my calculator real quick. I'm getting 416. So that's going to be the least distance we could have possibly traveled in that 10-second interval. So now let's repeat the whole process and do an upper limit. So if we're going to do an upper limit, then we're going to do the same idea we did with the lower limit, except we're going to always choose the larger of the velocities, the fastest we went over that 2-second interval. So that means we're going to start with the 36 times 2, and then we're going to take the 40 times the 2, and then the 48 times 2, and the 54 times 2, and finally we'll do the 60 times 2. So we can add all of these up, and I'm going to pause it here a moment and get that. And I'm getting 476 feet. So this is the greatest distance we could possibly have traveled if we went actually the fastest over each 2-second interval that we went over the entire interval. Now, if we choose that lower estimate, what is the maximum amount our estimate could be off? Well, we know that certainly the worst we could be off would be the greatest distance we traveled minus what our estimate is. So the greatest we could have been off is 60 feet. Probably less than that, but that's the most we could be off. So now what we're going to do is repeat this process again, and we're going to make up data and put in time values for t equals 1, 3, 5, 7, 9. And on these, we're just going to make up data, like I said, but we're going to continue this non-decreasing aspect, and we don't want to make it too predictable. So it's going to turn out it won't really much matter. So I'm going to say, just making this up, you could do something different, it won't matter. I'm going to say maybe we went 31, and then 38, and then 43, and then 52, and then maybe 59. So let's look at what now the upper estimate would be. So now our time interval here is 1 second. So over that first second, if we take the fastest we ever went, that is 31, times 1, plus then over the next 2-second interval, if we took the fastest we went, 36 times 1, and then we would get 38 times 1, and then we're going to get 40 times 1, and then we'll get 43 times 1, and then we're going to get 48 times 1, and 52 times 1, and 54 times 1, and 59 times 1, and the fastest on that last interval is 60 times 1. Now, I'm not even going to multiply those out yet because I want to make the point here. Now, the lower estimate is going to be, I'm going to now go through and do the same thing. I'm going to try to create a little space if I can. I'm going to move this over just a little bit. Let me come back with the eraser I want. So let me say now that the lower estimate is going to be, so I'm going to start with the 30 times 1, and then notice the next one is going to be the same as the one above it, and likewise these are all going to be the same, the lower estimate and the upper estimate. the distance we travel, we're just off one interval. So I'm going to stop at the end here, one before where I stopped with the upper estimate. So I'm not going to use the 60 for that last interval. Well, now if we imagine what's the greatest our error could be, we would subtract these. And if you imagine subtracting these, what we're going to get is all of these are going to cancel each other out, except that we're going to get the 60 times 1 minus the 30 times 1. That is, we're getting the largest value of s minus the lowest value of s times our delta t. Notice that's what we got on the first one. Remember, we got here that same idea. We would have gotten the 60 minus the 30, and there our delta t was the 2. And so that's why we got on that one the 60. So if we think about this, we can see that our error, this, remember, is our maximum error, and that error we can at least theoretically control by choosing the size of our delta t. The smaller increments we take on our measurements of time, the smaller our error is going to be as we add up those areas under the curve using rectangles. That's a hugely important idea there. Okay, we can get as much accuracy as we want by choosing a small enough delta t. We can get as much accuracy as we want by choosing a small enough delta t. Okay, so let's slide down here and expand our ideas here. So let's look at positive and negative velocities. So suppose a particle moves right at a constant velocity of 30 feet per second for 5 seconds, then moves left at 20 feet per second for 30 seconds. So we can show moving right as a positive 3 for those first 5 seconds, and you can see a visual of the distance that we travel by the area of that rectangle. If we then move left at 20 feet per second for 3 more seconds, then you can see that as that negative velocity as being this rectangle that is below the x-axis. So if now we can ask different questions here. We can see that the area above the x-axis is that, what would we say, 30 times 5. So that's 30 times 5 is 150. So that represents then that 150 feet we move to the right. The area below the x-axis is going to be that 20 times that 3, which is going to be 60 feet we moved back to the left. So if we think of that as being a net change in position, so the net change in position of our particle, which we will call displacement, is going to be that positive 150 minus the 60. So that is, we're going to end up at the end of that 8 seconds being 90 feet right of wherever we started. So that net change in position, that displacement, is going to think of that area above the curve as being positive and that area below the curve as being negative. If we want to know a different question, what is the total distance traveled? So if here we don't care about whether we're going right or left, but we just want the distance we traveled over that 8 seconds, then we don't care if we're going right or if we're going left. We would say the total distance we moved is going to be 210 feet. And so you're going to see that these are different questions that we will be asked in this particle motion idea at different times. Okay? Okay, so now in general, if we want to find the distance traveled for a non-negative velocity, then we want to find the area from t equals a to t equals b under the velocity curve. So what we're going to do then, we're going to do what's called partitioning. We're going to partition the t-axis from t equals a to t equals b into, we're going to say, n subintervals, n subintervals of equal width. So that is our delta x, or delta t, I guess we're calling it right now. Our delta t is going to be that b minus a divided by n. That's going to be the width. So we're going to imagine we're going to go, 1, 2, 3, 4, however many it takes till we get to n of these subintervals. Then what we're going to do is we're going to name these. So I'm going to call the left one t sub 0. Then that one right there is going to be t sub 1 and t sub 2 and so on. And we're going to end up with the last one is going to be our t sub n. So then what we're going to do is one of two things. We can either make these into rectangles where we choose the left side to be the height of the rectangle, or we might think of the right side of that subinterval as giving us the height of the rectangle. And so we will say if we're using the left ones, so we can approximate that total distance. So I'm going to say the total distance is going to be approximated by, and we would take then that v of, and if we're doing I'm going to say this is going to be our left rectangles right here. So we're going to use that left side right here to get the height. So that would be v of t sub 0. That would be the height of that rectangle times our delta t. That's going to be the width. Then we would go to the next rectangle and say that's going to be v of t sub 1 times delta t, and we would keep doing this until we get to, and if we're doing left rectangles, we're going to end up right here, which is going to be v of, I'm going to call that t sub n minus 1 times delta t. Now we can write that in summation notation, writing that as sum, and I'm going to say I going from 0 to n minus 1 of v of t sub I times r delta t. And if we were going to do I'm going to change colors here. Suppose we were going to do a right rectangles there. So now we're going to take the right side of each of those subintervals and plug that into our velocity function. Then our first one would be t sub 1 times that delta t, and the second one would be t sub 2 times delta t, and we would end up with that last one being right there at b, which we're going to call v of t sub n times delta t, and that would make our summation be I going from 1 to n of v of t sub I times r delta t. So these we are going to call, whichever form we use here, we are going to call these Riemann sums. When we use these rectangles to approximate the area under a curve, we're going to call those Riemann sums. Very good.